Welcome to iLecture Online, and here's a really interesting example of how to use torque problems on the human body. All right, I drew very cryptically here the forearm. Oh no, here's the forearm and the upper arm and the biceps of a person. So my drawing skills aren't that good, but at least cryptically I can kind of get the message across. And the interesting thing about the bicep is at the very top, where it's connected to the shoulder and the humerus, the upper arm bone right here, it's attached pretty well close to the bone right here. But over here, it's attached about 4 centimeters away from where the elbow has its joint, where the elbow joint is. And so the bicep is actually attached to the forearm bone right here at a distance about 4 centimeters away from the joint, which is about 1.5 inches away. And so in order for the arm then to work, the bicep needs to pull to bring the arm up, and then the tricep in the back then pulls back this way to get the arm back down. Of course, gravity itself can do that already, but to bring the arm up, your bicep has to do that. And then, of course, when you put a weight in your hand, so when you're doing barbells like this, then of course the bicep has to work extra hard. So the question then becomes, what is the force required on the bicep if the barbell weight has a weight of 40 pounds, and let's say that the forearm has a weight of about 3 pounds? Assuming the length from the distance from the joint in the elbow to where the barbell is held is about 35 centimeters, and then assuming that the center mass of the forearm is roughly at the halfway point between the hand, the middle of the hand, the palm of the hand, and the elbow joint. So, taking that as assumptions, find the force on the biceps. And of course, this is a typical torque problem. That means that the sum of all the torques about some pivot point has to add up to 0. And let's make the pivot point right here the joint in the elbow. And now we have to find all the forces that act on that, causing torques about the elbow joint. So the first force would be the weight of the barbell right here. That would be the big mg. And then the distance from the line of action of the force to the pivot point right here, the perpendicular distance, is this distance right here. Let's call this distance d1. Okay, then we have the weight of the forearm, so we assume that to be at the center mass at the halfway point. So right here we have the mg of the forearm, and then the distance, the perpendicular distance from the point of rotation, from the pivot point to the line of action of the force, which is right here. That would be distance d2. Okay, and then we have a third force, which is the bicep, which pulls upward in this direction. So that would be the force right here. And the distance from the pivot point to the line of action of the force. Now notice there's a slight angle in there. And for this particular purpose, we're going to ignore the angle because it's almost straight up. It's not going to be much of a difference because the angle is so small, so we can probably just ignore it. So we just simply have to worry about this distance right here from the point where it's attached to the pivot point right there. And let's call this distance d3, which was given as 4 centimeters. All right. Knowing that, let's now go ahead and write our equation. So 0 is equal to the 3 torques. The first one is the mg, and again, I'm going to consider a positive torque to be clockwise and a negative torque to be counterclockwise. Notice that the weight of the barbell will cause the arm to move in this direction, which is a clockwise direction, which is a positive torque. So it's plus big mg times d1, the distance from here to the pivot point, plus because the weight of the arm will also cause a positive torque, so plus the little mg times d2. And now notice that the bicep will pull in the opposite direction, trying to pull the arm upward, which is a counterclockwise direction, so it's a minus the force on the bicep times the distance d3. All right, and now we have to solve that equation for F. So let's move the f d3 over to the other side. So we have f d3 is equal to mg d1 plus little mg d2. And then finally divide both sides of the equation by d3, like so. And now we have an equation ready to solve for f. We, of course, need to plug in what these numbers are equal to. So let's do that. So we have the force is equal to the weight of the barbells, which is 40 pounds, times the distance d1, and that would be the entire distance of 35 centimeters. Now here you may say, well, wait a minute. Why am I mixing pounds and centimeters? You can't do that. Well, in a way we can, because eventually, since we're going to divide the right side by d3, the units of centimeters will disappear and we're simply left with pounds, which is the unit for force. So we can actually do that. It's okay to mix it. Although every time you do that, just make sure you're okay with that the units properly cancel out. So now we have the weight of the forearm, which was 3 pounds. And the distance to the pivot point from the center mass, that would be half the length of the forearm, which is half of 35 centimeters, which is 17.5 centimeters. And then divide the whole thing by distance 3, which is the 4 centimeters, where it's attached to the forearm and to the pivot point, that is 4 centimeters. Notice that centimeters here cancel out with centimeters down below. And now with the calculator, let's find out how much force a bicep requires to lift a 40-pound barbell. I think you're going to be surprised. Let's see, 40 times 35 plus 3 times 17.5, and then divide that by 4, and it's 363 pounds. So the force on your bicep is 363 pounds. That's quite surprising. A lot more than what you're actually lifting. So think about that. Simply lifting a 40-pound barbell like that with one arm requires a force of 363 pounds in your biceps. Your muscles are a whole lot stronger than you thought they were. All right, but that's how you do that problem. Let's see if I can come up with another interesting example.